A plumber today might fight a leak for hours. 2,000 years ago, Roman engineers built water systems that ran flawlessly for centuries. Their secret was not just grand aqueducts, but something far more intricate and hidden. This is the story of Roman pipe joinery, the ancient art of connecting the empire. By the end, you will understand the precise engineering that made an entire civilization flow. We will uncover how they sealed pipes without modern glue and ask if their favorite materials secretly poisoned them. What does it take to build something that outlasts an empire? Think of it as the hidden nervous system of a vast, living empire. Roman pipe joinery was the precise craft of connecting sections of pipe to create continuous, leak-free channels for water, waste, and heat. This was not just about laying pipes end to end. It was a sophisticated engineering discipline that solved a fundamental problem: how to move a liquid under pressure across miles of terrain and through the walls of countless buildings without losing a single drop. Every connection was a potential point of failure, a tiny gateway for disaster. A single leak could undermine a foundation, flood a street, or deprive an entire neighborhood of fresh water. So the Romans treated each joint not as a simple coupling, but as a critical engineered component. They developed a whole toolkit of solutions, from simple sleeves and clamps to complex, lead-sealed fittings, each designed for a specific purpose, whether it was carrying cold spring water into a public fountain or channeling scalding steam through the floors of a bathhouse. This joinery held everything together, from the grandest aqueduct terminus to the humblest kitchen drain. And within these seemingly mundane connections lie some of Rome's most fascinating engineering secrets, and its most enduring mysteries. The empire's flowing veins were not made from a single substance. Romans mastered a surprising variety of materials, each chosen with a clear and calculated purpose. The most infamous of these was lead or plumbum, the very root of our word plumber. They used it everywhere, from the massive municipal mains to the delicate pipes inside wealthy homes. Why choose a metal we now know is poisonous? The answer lies in its nearly perfect workability. Lead is soft, melting at a relatively low temperature. A Roman craftsman could easily pour molten lead into a mold to create a custom fitting, or hammer a sheet into a seamless tube. Most importantly, it could be welded cold. To join two lead pipes, a worker would simply hammer the edges together, fusing them into a single, continuous piece without a single seam. This created a joint that was, for all practical purposes, monolithic and perfectly watertight. It was the ultimate imperial material, malleable and obedient, bending to the will of Roman engineering. Yet this convenience came at a hidden cost: a slow, insidious leak of a different kind into the bodies of those who drank from it. For broader, less pressurized applications, the Romans turned to fired clay or terracotta. These pipes were crafted on large wheels, shaped into long cylindrical sections, and then baked in kilns until hard. Each section had a flared end, like a bell, designed to receive the straight end of the next pipe. The joint was then sealed with a simple mortar mix. This method was far cheaper and less labor-intensive than working with lead, making it ideal for the extensive drainage systems beneath city streets and for the vast networks of aqueduct channels that cross the countryside. While not as strong under high pressure as lead, terracotta was incredibly durable and resistant to corrosion. Many of these clay pipes, buried for millennia, are excavated still intact, a testament to the longevity of this humble technology. And in some surprising places, they even used wood. Hollowed-out logs, often elm or pine, were bound with iron hoops and used for short-distance water transport, particularly in mining operations or temporary military camps. It was a quick, renewable solution for moving water where permanent infrastructure was not yet established. This material triad reveals a sophisticated and pragmatic approach. Roman engineers were not dogmatic. They selected the right tool for the job, weighing cost, performance, and local availability, building a hydraulic empire one calculated decision at a time. But mastering the material was only half the battle. The true genius and the deepest mystery lay in how they made these disparate parts hold together against the relentless push of water. That soft, workable lead had a sinister side. For generations, a haunting question has lingered in the halls of history. Did the Romans, in their engineering triumph, unknowingly poison themselves? The theory is compelling and grim. They used lead not just for pipes, but for cooking pots, wine sweeteners, and even as a cosmetic. With every sip of water that sat in a lead cistern, with every gulp of wine doctored with lead acetate, could a toxic dose have been slowly accumulating in the bodies of the Roman elite, sapping their vitality and clouding their judgment? Some historians point to the erratic behavior of later emperors, the political instability, and the cognitive decline that seemed to plague certain powerful families as potential symptoms of a society suffering from low-grade, chronic lead poisoning. It paints a tragic picture of an empire engineering its own neurological downfall. But is the case solid? Modern science has begun to sift through the evidence. Analysis of ancient Roman bones from burial sites, particularly from affluent areas where lead plumbing was common, does show elevated lead levels compared to prehistoric populations. Sediment from the bottom of Roman water tanks has also been tested, confirming that water sitting in lead conduits did indeed leach the metal. The exposure was real. Yet the verdict is not so simple. Many experts now argue that the levels, while higher, were likely not high enough to cause widespread societal collapse. The calcium-rich water from Roman aqueducts, flowing quickly through pipes, would have coated the interior with a protective mineral layer, significantly reducing lead leaching. The real danger may have been in the concentrated, homemade wines and sauces, not the municipal water supply, and the empire's decline was a sprawling tapestry of military overextension, economic inflation, political corruption, and external invasion. To pin it all on a single element, however poetic the irony, might be an oversimplification. The truth lies in a nuanced middle ground. Lead was a silent, slow-acting toxin in their world, a background risk that certainly harmed individuals, especially the wealthy with their elaborate plumbing and treated delicacies. But it was likely one thread in a much larger tapestry of decay, a hidden flaw in the magnificent machine they built, not the sole switch that turned it off. The true artistry of these connections was forged with a remarkably familiar set of tools. To shape lead, a Roman plumber or plumbarius would have reached for a soldering iron, though his looked nothing like the electric pencil of today. It was a heavy iron rod, heated in a charcoal brazier until its tip glowed a dull red. With this simple tool, he could carefully melt and fuse lead seams, creating watertight seals at junctions and repairs. His hammer was not for brute force, but for precise, cold welding. By skillfully tapping the soft edges of two lead pipes together, he could molecularly bond them, a technique that required a steady hand and an intuitive feel for the metal. Chisels and saws were for cutting and trimming, ensuring each pipe end was perfectly square for a tight fit. And perhaps most telling of all, They used the libra, a simple but effective plumb level. This tool, a weighted string suspended from a frame, proved that the Roman obsession with precision extended even to the flow of water. A pipe laid with perfect gravity-fed slope meant efficient, silent movement. A miscalculation meant stagnation, sediment buildup, and eventual blockage. Their toolkit reveals a profound truth. While their materials and some methods are alien to us, the Roman plumber's mindset was thoroughly modern. He was a problem solver working to exacting standards, relying on skill and proven instruments to turn theory into enduring reality. But with the pipes laid and the joints sealed, one final, critical question remained. How did they know it was actually working? The brilliance of Roman leadwork reached its peak not in the pipe itself, but in the joint. To connect a pipe to a fitting or to seal a complex junction, they employed a technique that would look remarkably familiar to a modern electrician or plumber. They used solder. This was not the simple melting of pure lead, but a sophisticated alloy, typically a mix of lead and tin. The choice was deliberate. Pure lead melts at around 620 degrees Fahrenheit, a temperature that could easily warp or damage the thin walls of the pipe being joined. By adding tin, which melts at a much lower 450 degrees, they created a workable alloy that flowed like thick honey at a safer, more controllable heat. The craftsman's skill was in managing this liquid metal. First, he would meticulously clean the surfaces to be joined, scraping them bright to ensure a good bond. Then, using a flux, often just pine resin or tallow, he would coat the area. This crucial step prevented oxidation during heating, allowing the molten solder to wet the surface perfectly. With his heavy soldering iron glowing from the coals, he would touch it to the joint, heating the lead pipe itself. Only then would he apply the solder stick, watching as the alloy melted and was drawn by capillary action into the narrow gap between the pipe and the fitting. It was a dance of heat and timing. Too little heat, and the solder would bead up and not flow, creating a weak, porous seal. Too much heat, and you risked melting the underlying pipe, causing a collapse or a blowout. The goal was a smooth, concave fillet of hardened metal that completely ringed the joint, a silvery band of absolute security. When done correctly, this soldered seam was as strong as the pipe itself, capable of withstanding the constant pressure of flowing water and the subtle shifts of the ground for centuries. It was a testament to their understanding of metallurgy and physics, a hidden precision in the guts of their empire that turned a potential weakness into one of its greatest strengths. While lead required a master's touch with fire and metal, terracotta demanded the patience of a potter and the foresight of an architect. These clay pipes began as nothing more than wet earth, dug from riverbanks or quarries. A skilled craftsman would wedge and knead the clay to remove air bubbles, then throw it onto a large, slow-turning wheel. As the wheel spun, he would shape the viscous material into long, hollow cylinders, carefully tapering one end to a slightly narrower diameter. This was the spigot. The other end he would flare outward, forming a wide, bell-shaped socket. Once shaped, the damp pipes were left to dry slowly in the shade, a crucial step to prevent cracking. Only then were they loaded into a kiln, stacked with care, and subjected to a roaring fire that baked them for days, transforming soft clay into a hard ceramic shell. The firing process was itself a delicate balance. Too cool, and the pipe would remain porous and weak. Too hot, and it could warp or even vitrify, becoming brittle glass. The goal was a perfect, resonant ring when tapped, a sign of uniform strength. This mass-produced modular system was the workhorse of Roman hydraulics. To join them, the process was elegantly simple. A worker in a trench would take a pipe and coat the plain, tapered spigot end with a wet mortar mix, often lime and crushed terracotta or pottery shards. He would then insert this spigot into the bell-shaped socket of the pipe already laid in the ground. The mortar acted as both lubricant and sealant. As he pushed the pipes together, the excess mortar would squeeze out around the rim, which he would then smooth with his thumb, creating a continuous gasket. For added security, especially in pressurized lines, the gap around the joint might be packed with oakum, a fibrous material, before a final cap of mortar was applied. The genius was in the taper. It ensured a tight, wedged fit that grew more secure over time as the mortar cured and the surrounding earth settled. Water flowing through would actually help the seal by causing the mortar to develop a self-healing crystalline structure. This was not a high-tech solution, but a profoundly durable one. It relied on geometry, chemistry, and the timeless properties of earth and fire. While a lead joint was a permanent weld, a terracotta joint was a flexible, breathing connection, allowing the entire network to shift slightly without shattering. A humble yet brilliant adaptation for an empire built to last. But for all the permanence of lead and terracotta, Rome also mastered a more transient art. In the damp forests of northern Europe, or the hastily built confines of a new military fort, their engineers turned to the most abundant material of all, wood. Imagine a legion on the march, needing to bring fresh water from a nearby stream into their fortified camp. Stone aqueducts were impossible, and hauling heavy clay pipes was impractical. The solution was as old as humanity itself, yet refined with Roman efficiency. They would select straight, mature logs, often elm for its resistance to rot or pine for its workability. Using long augers, drills sometimes powered by water wheels, they would bore a hole straight through the heart of the tree, creating a natural, continuous channel. The ends of these wooden pipes were then carefully tapered on a lathe, so that the narrow end of one log could be driven tightly into the widened socket of the next. For a stronger seal, they would sometimes wrap the joint in soaked leather, which would shrink as it dried, cinching the connection like a vise. In more permanent installations, blacksmiths forged simple iron collars, bands that were heated until they expanded, slipped over the joint, and then cooled to clamp the wood in an unbreakable grip. These wooden pipelines were not for high-pressure city mains. They were the veins of frontier outposts, mining operations, and temporary settlements, moving water with a quiet, organic efficiency. The beauty of this system was its simplicity and sustainability. A damaged section could be replaced by felling a new tree, a technology that moved with the army and left a light footprint on the land. It reveals a facet of Roman engineering often overshadowed by their marble monuments, a profound adaptability. They were not just builders of eternal Rome, but masters of the provisional, capable of crafting order from the wilderness with nothing but an axe, an auger, and relentless ingenuity. Yet all this meticulous craftsmanship, from lead welds to clay sockets, served a single grand purpose. It was the final, critical link in a chain that began miles away in Mountain Springs. The soaring arches of an aqueduct are the empire's most famous silhouette, but they were merely the delivery system. The true challenge began where the open channel ended, at the terminal tank inside the city walls. Here, the vast, gravity-fed river of water had to be tamed, divided, and directed. This was the moment of truth for Roman pipe joinery. Imagine that terminal tank, the Castellum Divisorium, as a massive stone distribution hub. The main aqueduct channel poured its contents into this basin, but from there, the water did not simply spill out. Instead, a series of precisely placed outlets, each fitted with a bronze regulating valve or a carefully sized lead pipe, tapped into the supply. This is where the network fractured into 1,000 capillaries. The largest pipes, often lead, would branch off to supply public fountains, bathhouses, and imperial palaces. Smaller lines would peel away to feed neighborhood cisterns or the private homes of the wealthy. Every one of those branches required a secure, leak-proof joint. A failure at this junction meant water pressure dropping across an entire district, or worse, a catastrophic flood undermining the foundation of the distribution tank itself. The joinery here had to be perfect, engineered to handle not just the static weight of water, but the dynamic surge as flows were switched and redirected. The pipes leaving the castellum were the roots of an invisible urban tree, and every joint was a knuckle in that root system, holding firm against the constant push from above. Without this hidden web of reliable connections, the aqueduct's magnificent journey would have ended in a useless, stagnant pool. The joinery translated imperial scale engineering into a personal utility, turning a marvel of concrete and stone into a clean drink for a child at a street fountain. It was the silent, essential translator between the monumental and the mundane. But controlling this flow was a constant battle against an invisible force. Water is not a passive substance. It moves with weight and momentum, and in a closed pipe, that energy translates into pressure. For Roman engineers relying solely on gravity, managing this pressure was a delicate, high-stakes equation. Too little, and the water would stagnate, allowing sediment to settle and block the narrow pipes. Too much, and the relentless force could blow apart a poorly made joint, rupture a pipe wall, or surge uncontrollably out of a public fountain. Their entire system was a masterpiece of calculated restraint. The primary tool was the gradient, the gentle, unbroken slope from the source spring to the destination city. This slope had to be perfect. Surveyors using simple but effective tools like the courbates, a long, water-leveled wooden frame, would map a route dropping only a few feet per mile. This created a steady, predictable push, just enough to keep the water moving. But within the city, this consistent slope became a problem. As pipes branched off and descended into neighborhoods, that gentle push could turn into a dangerous hammer. So they introduced pressure brakes. Water would be channeled into a large, open settling tank at a high point. Here, the pressure would dissipate as the water simply filled the basin. From this new, lower starting point, a new pipe would begin its downward journey, resetting the pressure clock. It was like a series of stair steps for water, each landing calming the flow before sending it down again. Pipe diameter was another critical variable. A wider pipe allows more water to pass, but it also reduces velocity and pressure. A narrower pipe increases speed and force. By strategically varying the diameter of lead pipes or the channel size in aqueducts, they could throttle the flow to match the need. A major bathhouse requiring a torrent for its pools would get a large diameter feed. A private residence might receive water through a pipe no wider than a modern garden hose. And everywhere, they used the humble overflow. Public fountains were designed to run continuously, the excess water spilling out and draining away. This constant discharge acted as a natural pressure release valve, ensuring the system never built up to a breaking point. It was a dynamic, living network, engineered not for a single static condition, but for the ever-changing demands of a thirsty city, all held together by those silent, steadfast joints. The hidden life of a Roman water pipe began not as a tube, but as a flat sheet. This was the fistula, the empire's standard issue artery. Craftsmen would cast molten lead into large, rectangular plates, each about 3 feet long and 1.5 feet wide, and roughly 1/8 of an inch thick. These sheets were surprisingly manageable, a blank canvas for hydraulic engineering. To transform this flat slab into a pipe, a worker employed a technique both simple and brilliant. He would place the sheet over a cylindrical wooden mandrel, a form the exact diameter he desired for the pipe's interior. Then, with careful, practiced blows of a mallet, he would roll the soft lead around the form, bending the edges upward until they met in a straight seam running the entire length. The final step was the cold weld. Using a special rounded hammer, he would meticulously tap the 2 edges together, fusing them into a single, unbroken line. The seam was not soldered, it was literally hammered into molecular unity, making the joint as strong as the parent metal. The mandrel could then be slid out, leaving behind a perfectly cylindrical, seamless-looking tube, ready for installation. This rolling method allowed for incredible flexibility. By using different mandrels, they could produce fistulae in a range of standard diameters, from about 1 inch for household supplies to over a foot for major municipal lines. But these pipes were not anonymous. Before the lead sheet was even rolled, it often received a unique signature. Using a set of metal punches, a worker would stamp the soft surface with inscriptions. These marks were a permanent record etched into the metal itself. Some bore the name of the plumber's workshop or the foundry that cast the lead, a stamp of craftsmanship and a form of ancient branding. Others indicated the pipe's owner, often an emperor, a senator, or a city, declaring this stretch of conduit as imperial or municipal property. More practically, some stamps recorded the pipe's length, weight, or even the name of the overseeing magistrate who approved the work, creating a chain of accountability that stretched from the quarry to the aqueduct. These inscriptions turned a simple pipe into a historical document. When archaeologists excavate a broken fistula, they are not just finding a piece of plumbing, they are reading a label. That stamp might tell them this pipe was commissioned by the Emperor Nerva, or that it was part of the renovation of the baths of Caracalla. It is a direct, tangible link to the specific moment and the specific hands that built this part of Rome's circulatory system. The fistula was a marvel of mass production and individual artistry, a stamped and hammered testament to an empire that documented its infrastructure as carefully as it built it. Each stamped and hammered fistula was a solitary length, useless until connected to another. To bridge these gaps, Roman engineers developed a specialized vocabulary of joints, each design a precise answer to a specific mechanical challenge. The most fundamental of these was the socket and spigot, the workhorse of terracotta systems. As we've seen, one pipe ended in a flared bell, the socket. The next pipe had a plain, tapered end, the spigot. Smeared with mortar and pushed home, this created a strong, flexible connection. Its genius was in its forgiveness. The mortar seal allowed for slight movement as the ground settled, and the taper ensured a tight, self-sealing fit that grew stronger under the pressure of flowing water. This was a joint for the long haul, designed for the slow, patient networks of drains and aqueduct channels that snaked beneath the empire. For the pressurized world of lead pipes, a more permanent bond was required. Here, the soldered sleeve joint reigned supreme. This was not merely a coupling, it was a fabricated component. A craftsman would take a short, wider diameter section of lead pipe and carefully split it down one side. This sleeve would be opened like a clamshell and fitted over the butted ends of the two pipes to be joined. The seam of the sleeve itself would be soldered shut, and then the critical step, the craftsman would solder the entire circumference of both ends of the sleeve to the pipes beneath, creating two continuous, watertight rings of solder. This created a robust, reinforced connection that could handle significant internal pressure and resist bending or pulling forces. It was the standard for most inline connections in lead systems, a testament to their mastery of fluid dynamics and metallurgy. But where immense forces or frequent maintenance were expected, they deployed a more advanced solution, the flange joint. Picture the end of a large lead or bronze pipe not as a simple cylinder, but flared outward into a flat, perpendicular rim like a collar. The pipe it connected to had an identical flange. Sandwiched between these two metal faces was a gasket, likely made of lead sheeting wrapped around hemp or leather. The two flanges were then bolted together with iron bolts, compressing the gasket into a perfect seal. This was engineering on an industrial scale. Flange joints were the connectors of the hydraulic world, used at the base of massive public fountains where water hammer was constant, or at the junctions where different aqueduct lines met in a distribution tank. Their advantage was revolutionary serviceability. If a section of pipe needed repair or replacement, workers could simply unbolt the joint, rather than having to cut out and resolder a permanent seam. This design speaks to a forward-thinking mentality, an anticipation of future need that is startlingly modern. From the humble, mortared taper of terracotta to the bolted, gasketed might of a flange, each joint type reveals a layer of Roman intent, a calculated response to the silent, relentless demands of moving water. Metal and mortar were not the only guardians of Rome's watertight seal. While a soldered lead joint was a permanent fusion, many connections demanded a different kind of defense, one that could flex, absorb shock, and adapt. For these, Roman plumbers turned to a sophisticated arsenal of sealants, each a carefully formulated barrier against the persistent threat of the drip. The most common of these was not a modern synthetic, but a humble yet miraculous mortar. They mixed slaked lime with a volcanic ash known as pozzolana, mined from the hills around Pozzuoli. When combined with water, this mixture did something extraordinary. Instead of simply drying hard like ordinary plaster, it underwent a chemical reaction with the water itself, forming a crystalline structure that was not only incredibly strong but actually waterproof. Even more astonishing, this concrete could cure underwater, making it perfect for sealing the joints of submerged pipes or lining cisterns. A terracotta pipe joint packed with pozzolana lime mortar didn't just plug a gap, it chemically bonded to the ceramic, creating a seal that grew more resilient over centuries as the reaction continued slowly within. For the critical joints in lead systems, especially where pipes met stone basins or where slight movement was expected, they used lead wool. This was exactly what it sounds like: fine strands of lead scraped or pulled into a tangled, fibrous mass. Packed tightly into a joint before soldering, this wool acted as a malleable gasket. It would compress to fill any irregularity, and when the hot solder was applied, the outer strands would melt and fuse with the main solder seam, while the inner core remained a pliable, water-blocking mass. It was the perfect combination of flexibility and ultimate security. Then there was oakum, a material with a history as long as shipbuilding. This was simply hemp fiber, the tough strands of the cannabis plant, soaked in pitch or pine tar. Oakum was the plumber's duct tape, driven into the gaps around pipe penetrations through walls, or used as a primary seal in low-pressure drains. The dry hemp fibers would swell dramatically when wet, creating a tight mechanical seal. The pitch coating made the mass water repellent and resistant to rot. This humble, tarry rope was the first line of defense in countless forgotten connections, silently expanding in the dark to choke off leaks before they ever began. Each sealant was a targeted solution: pozzolana mortar for permanent structural bonds, lead wool for high-pressure metal-to-metal interfaces, oakum for flexible, forgiving closures. Together, they formed a layered defense, ensuring that even if a primary joint shifted or a solder seam developed a hairline crack, a secondary seal was already in place, waiting. This redundancy reveals a profound understanding of failure. The Romans didn't just build joints to be perfect, they built them to be resilient, anticipating the slow sigh of settling earth and the relentless patience of water. These stamps were more than just labels. They were a direct line of accountability. When a Roman craftsman hammered his mark into a soft lead sheet, he was not merely signing his work, he was legally binding himself to it. That stamp, often a simple name or a workshop symbol, was a permanent guarantee. If that pipe failed and caused a flood in a wealthy patron's home, the stamp told the authorities exactly whose door to knock on. This practice transformed anonymous infrastructure into a network of named responsibility. It created a powerful incentive for quality because a plumber's reputation and his livelihood were quite literally stamped onto every length of pipe he produced. But these marks, known as plumbum inscriptions, could reveal far more than just a craftsman's name. Some of the most common stamps bore the name of the reigning emperor. A pipe might read, "Property of the Emperor Trajan," or "Under the authority of Nervus Caesar." This was not necessarily because the emperor personally ordered a bathroom renovation. Instead, it signified that the lead itself was imperial property, mined from state-controlled mines like those in Roman Britain or Spain. The pipe was a piece of the emperor's wealth, deployed for public works or for installations in state buildings. It was a silent declaration of imperial power and beneficence, a metal receipt proving that the ruler's resources were flowing directly to the people. Other stamps pointed to the complex business of water rights. Inscriptions sometimes named a specific individual who held the equi concessio, the water concession. This was a lucrative license granted by the state, allowing a private citizen to tap into the main aqueduct line and run a private pipe to their villa or commercial operation. The stamp on that private pipe proved the connection was legal and paid for, distinguishing it from an unauthorized, clandestine tap. It was the ancient equivalent of a utility company tag on your meter, a way to prevent theft from the public water supply. Decoding these stamps today is like piecing together a fragmented economic ledger. A single pipe might tell us that the lead came from the Mendip mines in Britain, was shipped to Rome under the reign of Vespasian, and was finally installed by the workshop of Lucius Seius for a private concession holder named Marcus Agrippa. That is 3 layers of history, commerce, and personal identity, all pressed into a soft metal sheet 2,000 years ago. These humble marks turn archaeology into detective work, allowing us to trace not just the flow of water, but the flow of authority, commerce, and social contract through the very veins of the empire. A different kind of pipe network did not carry water but warmth. While aqueducts fed the baths, a separate, hidden circulatory system heated them from within. This was the hypocaust, Rome's ingenious central heating, and its joinery was a masterpiece of hollow ceramic architecture. The floors we have already seen, raised on brick pillars to allow furnace air to flow beneath. But the true genius extended upward into the very walls. To capture every bit of heat, Roman builders lined the walls of bathhouses, and wealthy villas with special hollow bricks called tubuli. These were not pipes in the traditional sense, but rectangular box tiles, typically about a foot square and a few inches thick, with an open front and back. The magic was in their assembly. A worker would stack these tubuli vertically, one directly on top of the other, creating a continuous, hollow column from floor to ceiling. But a simple stack would let the hot air rush straight up and out, wasting the heat, so the joinery was deliberately imperfect. Each tubulus had a series of small, raised bumps or ridges on its top surface. When the next tile was placed on top, these bumps created a narrow gap between the two tiles, a controlled leak. Hot air from the hypocaust floor would enter the bottom tubulus, rise through the stack, but at each joint, a portion of that searing air would be forced sideways through these gaps, into the cavity behind the entire wall of tiles. This transformed the entire wall into a massive, gentle radiator, slowly releasing heat into the room rather than blasting it out through a chimney. The joints were not sealed, they were engineered to meter the flow, a breathtakingly elegant solution. For ceilings, they used a similar principle with teguli mammoty, roof tiles with nipples. These were flat tiles with small clay knobs, or mammy, at each corner. They were mounted to the ceiling with the knobs facing down, creating a narrow air gap between the tile and the ceiling itself. Hot air from the wall cavities would rise into this gap, transferring the last of its heat to the ceiling plaster before finally escaping. The joinery here was about creating space, not closing it. Every connection in this heating labyrinth, from the stacked tubuli to the nipple space tiles, was designed to slow the air down, to make it linger and give up its energy. It was a system of calibrated leaks and deliberate cavities, a stark contrast to the watertight seals of the aqueducts, yet born from the same inventive spirit. This hidden network in the walls turned stone buildings into cozy havens, proving Roman engineering was as much about comfort and control as it was about conquest and scale. A Roman bathhouse was a symphony of flowing water, and its plumbing was the intricate score. Step inside the bustling thermae on any afternoon, and you would experience the empire's hydraulic genius in its most concentrated form. This was not a single room with a tub, but a sprawling complex of pools, each demanding a different temperature, a different flow rate, and a different drain. The cold frigidarium, the warm tepidarium, and the searing caldarium all operated simultaneously, fed by a hidden, three-stream network of pipes that had to run in perfect, leak-proof harmony. Hot water, heated in massive bronze boilers over furnaces, rushed through its own dedicated lead pipes, insulated within the walls to preserve every precious degree of heat. Icy fresh water from the aqueduct arrived through a separate, cool line to feed the cold plunge pool and the drinking fountains. And everywhere used, soapy, and oily water had to be instantly whisked away through a vast subterranean web of large-diameter terracotta drains, all sloping perfectly toward the main sewer. The chaos of a public bath, with hundreds of patrons moving between these zones, depended entirely on the silent, flawless operation of this triple-layered system. A single failed joint in a hot water pipe could scald a bather or drain a pool. A clogged drain joint would cause filthy water to back up onto the elegant mosaic floors. The joinery here was not just about holding pipes together. It was about maintaining strict segregation. The hot and cold lines, often running parallel through the same service chase, could never meet or leak into one another. The waste lines had to be large enough to handle sudden surges, yet sealed tight enough to keep foul gases from seeping back into the bathing halls. Every connection, from the soldered sleeve on a pressurized hot feed to the mortared bell joint on a massive drain, was a critical component in a living machine. The bathhouse was the ultimate test of Roman plumbing theory, a place where engineering met daily human ritual, and where the quality of a craftsman's joints directly impacted the comfort, safety, and social order of the empire itself. Beneath the marble floors and elegant fountains, an entirely different kind of river flowed. The Cloaca Maxima, Rome's great sewer, was the dark twin to the aqueducts above, a sprawling underworld built to swallow the city's waste and stormwater. Its engineering challenges were monumental, not just in scale, but in sheer, brutal function. While aqueduct joints fought to keep pure water in, the sewer's joinery had to contain a corrosive, volatile mixture while withstanding the immense weight of the city above it. The materials here were chosen for endurance over elegance. The earliest sections, dating back to the Kingdom era, were built from massive, precisely cut stone blocks, forming a vaulted tunnel large enough for a man to walk through. Sealing these giant stone conduits was a task for the ages. Workers would fit the blocks together with such exactitude that the seams were nearly invisible, then pour a waterproof mortar made of lime and pozzolana into the joints from the inside. This mortar didn't just fill gaps, it chemically bonded with the stone, creating a monolithic, impervious shell that resisted both the acidic flow within and the damp earth pressing in from all sides. It was joinery on a cyclopean scale, where every seam was a potential gateway for collapse or contamination, sealed with a concrete that grew stronger with each passing century. As the system expanded, terracotta pipes of enormous diameter, some over 3 feet across, were incorporated for branch lines. The joinery for these behemoths used the familiar bell and spigot method, but everything was magnified. The mortar seal had to be perfect, as a failure here meant raw sewage seeping into the surrounding subsoil, poisoning the very ground the city stood on. The genius of the Cloaca's design, however, lay in its relentless, self-cleansing flow. Engineers gave the entire system a consistent, calculated slope, using gravity to create a swift current. This wasn't a stagnant pit, it was a flushing river. Seasonal rains would swell the flow, scouring the walls and joints clean of debris and sediment, a natural maintenance cycle built into the architecture. The joints themselves had to survive this periodic torrent, a hammering rush of water that could exploit the slightest weakness. To visit the Cloaca Maxima was to walk through the empire's guts, a testament to a civilization that planned not just for the light and the clean, but for the dark and the dirty. Its enduring stonework, still partially functioning today, stands as perhaps the ultimate proof of Roman joinery, a network that held firm against the weight of a city and the flow of its history. Even the most perfectly sealed joint could not last forever without care. For all its permanence, the Roman water network was a living system, one that required constant vigilance and skilled hands to keep it flowing. This was the world of the plumbarius, the plumber, whose craft extended far beyond installation into the critical arts of diagnosis and repair. Their first challenge was simply finding the problem. With miles of pipe buried beneath streets and behind walls, a leak could remain hidden for months, silently eroding soil or saturating a foundation. The solution was a simple but brilliant feature, the Putius or inspection shaft. These were vertical wells, lined with brick or stone, sunk at regular intervals along the aqueduct channel and at key junctions within the city. A maintenance worker could descend into a Putius with a lamp, listening for the hiss of a pressurized leak or visually tracing a line of mineral deposit that betrayed a slow seep. In larger sewers like the Cloaca Maxima, These shafts also served as access points for the plumbarii, the sewer workers, who would enter the dank tunnels to clear blockages of debris and silt, a filthy but essential task that prevented catastrophic backups. Once a problem was located, the repair methods showcased their pragmatic ingenuity. For a terracotta drain pipe with a cracked section, the solution was often a sleeve repair. They would carefully cut out the damaged segment and fashion a replacement piece from a new pipe. The new section would be inserted, and the two new joints would be sealed with fresh mortar, a straightforward patch that could restore function for decades. Lead pipes offered more options but required greater skill. A small pinhole leak might be fixed with a simple soldered patch, a piece of thin lead sheet hammered over the hole and fused into place with a careful touch of the soldering iron. For a more extensive rupture, they might perform a full sectional replacement. Using a saw, they would cut out the damaged length. Then they would prepare a new piece of fistula, cut to the exact size. The critical step was joining this new piece to the old, severed ends still embedded in the ground. This is where the soldered sleeve joint proved its worth. The plumber would slide a pre-made lead sleeve over one old end, insert the new pipe section, center the sleeve over the junction, and then solder both ends securely. It was a permanent, pressurized repair executed in a cramped, dark trench, a testament to their technical confidence. But perhaps the most fascinating repairs were the emergency ones, the quick fixes applied under duress. Archaeologists have found lead pipes with patches made not of lead, but of other metals, or even with holes simply plugged with a wooden dowel wrapped in oiled cloth and hammered in. These were the repairs of a system under stress, perhaps during a siege or a sudden freeze, showing that even the meticulous Romans sometimes had to make do. This ongoing cycle of inspection and intervention reveals a crucial truth. The empire's hydraulic marvel was not a static monument. It was a dynamic, managed utility, sustained by a forgotten army of skilled workers who knew every joint, every valve, and every whisper of the water that passed through them. The volcanic fury that buried Pompeii and Herculaneum in the year 79 created a tragic yet perfect archaeological snapshot. While the ash and pyroclastic flow froze moments of daily life, it also preserved the hidden workings of the cities in astonishing detail. The plumbing here was not crushed or looted, but suspended in time, offering us a street-level view of Roman hydraulic engineering that no other site can match. Walk through these silent streets today, and you can follow the water's journey from start to finish. You can see the lead distribution pipes, the fistulae, still embedded in the walls of houses, tracing their path from the street main into private courtyards. In the kitchens and lavish baths of wealthy villas, the bronze stopcocks and mixer taps remain in place, some even found in the on position, as if waiting for a servant to draw a bath that would never be filled. The joints are all there, exposed. You can see the soldered sleeve connections on lead pipes, the dark, silvery fillet of solder still intact after nearly 2 millennia. You can find the terracotta sewer pipes beneath the latrines, their bell and spigot joints sealed with mortar, still aligned in their gentle slope toward the main drain. This preservation allows archaeologists to answer questions that ruins alone cannot. They can measure the exact diameter of pipes to calculate flow rates for a specific home. They can analyze the mineral deposits, the sinter, inside a pipe to understand the water quality a particular family lived with. Most importantly, they can see the system in its full, messy reality. In Pompeii, we don't just see the engineering ideal, we see the practical adaptations, the repairs, and the compromises. A lead pipe might have a clumsy, obvious patch soldered over a leak. A downspout might be jury-rigged to divert rainwater into a cistern it wasn't originally designed to feed. This was a living, breathing utility network, constantly being tweaked and fixed by the local plumbarii. The evidence from these cities confirms the sophistication of the standard practices we've discussed, but it also reveals something more human. It shows the pressure points where systems failed, the corners cut by local builders, and the ingenious ways ordinary people interacted with the water flowing into their homes. The joints frozen in the ash tell a dual story, one of imperial engineering standards meeting the unpredictable needs of daily urban life. The principles hammered out in Rome did not travel as a rigid blueprint, but as a flexible set of ideas, bending to meet the demands of new lands. Roman engineering was not about imposing uniformity, it was about achieving function, and the joinery found in the provinces tells that story of brilliant adaptation. Take the damp, timber-rich frontier of Britannia. In Londinium, the Roman London, archaeologists have uncovered something astonishing, not a grand aqueduct, but a massive wooden water main. Fashioned from hollowed-out oak logs nearly a foot in diameter, these pipes were bound together with iron collars and sealed with pitch. This was not a primitive substitute, it was the perfect local solution. In a land where quality clay for terracotta might be scarce and importing heavy lead sheets was prohibitively expensive, the Romans turned to the endless forests. The joinery here was one of brute strength and organic sealants, creating a network that could be repaired or extended by any carpenter with an auger and an axe. It was Roman water management, built with a British accent, proving the empire could craft order from the wilderness with whatever materials lay at hand. Now, cross the Mediterranean to the sun-baked cities of Roman North Africa, like Leptis Magna or Carthage. Here, the story flips entirely. In these wealthy, arid provinces, water was not a convenience, it was life itself, and the joinery reflected that supreme value. They built not with wood, but with some of the most sophisticated and extensive lead pipe networks found anywhere in the empire. The dry climate and immense wealth from olive oil and grain exports funded hydraulic works on a staggering scale. The joints in these systems show a precision that often rivals, and sometimes surpasses, those in Italy itself. Archaeologists find exquisitely soldered sleeve joints, lead pipes stamped with the names of local magistrates, and complex distribution tanks that split flows with mathematical precision to feed countless public fountains and lavish bathhouses. In North Africa, Roman joinery wasn't adapted out of necessity. It was elevated to an art form, a display of civic pride and technological mastery in a landscape where controlling water meant controlling destiny. From the wooden mains of London to the gleaming lead webs of Carthage, this regional tapestry reveals the true genius of the system. It was a core philosophy, not a fixed manual. The empire provided the engineering principles, the relentless logic of gravity, slope, and secure connection. But the materials and the methods were left to the local environment, the available resources, and the specific needs of the community. A soldier in a damp northern fort drank from a wooden pipe sealed with tar. A merchant in a bustling African port washed in water, delivered through a lead pipe stamped with the city's seal. Both were served by the same Roman idea, executed with brilliantly local hands. This adaptive spirit is perhaps the most powerful secret of all, the reason their infrastructure didn't just conquer new lands, but took root and flourished within them. Then the lights went out. With the slow collapse of the Western Roman Empire, the steady hum of the aqueducts fell silent. The sophisticated empire-wide network of lead and terracotta did not vanish in a day, but its heart stopped beating. The knowledge of how to maintain it, the guilds of plumbarii who understood the cold weld and the pozzolana mortar, the administrative state that funded its upkeep, all fragmented and faded. What followed was not a sudden plunge into barbarism, but a long, slow retreat from complexity. The intricate joinery that had held an empire together became a lost language, and the art of moving water regressed to its most basic form. In place of the calibrated lead fistula, communities returned to hollowed-out logs, simple wooden troughs, and wells. The concept of a pressurized indoor water supply for the public good became a distant memory, a legend of a golden age. Castles and monasteries, the new centers of power, might have rudimentary plumbing, often just drains for waste, but the glorious, gravity-fed civic system was gone. The meticulous stamps of ownership and accountability were replaced by the anonymous work of a local carpenter. The soldering iron grew cold. This was more than just a loss of convenience. It was a contraction of possibility. The public bathhouse, that great social and hygienic equalizer, disappeared from daily life for centuries. The engineering principle of a continuous, sealed conduit under constant pressure was forgotten, replaced by the simpler idea of a container, a bucket, a well. You can see this regression in the archaeological record. In London, after the Romans left, the great wooden water mains they built rotted in the ground, unreplaced. The city's water supply collapsed back to the Thames and local springs, a source of contamination and disease. In Rome itself, the popes of the early Middle Ages struggled to patch a few remaining aqueducts, but the expertise was so diminished that they often failed, leaving the city to rely on the polluted Tiber River. The loss was not absolute, of course. In the Byzantine East, and later in the Islamic world, the hydraulic wisdom of Rome was preserved, studied, and even advanced. But in Western Europe, the peak had passed. The secure, watertight joint, that small triumph of engineering that enabled an urban civilization, became a ghost in the soil, a whisper of what had been. For nearly 1,000 years, the secret of how to truly bind a civilization together with flowing water was buried, waiting to be rediscovered. The silence of those buried pipes was finally broken not by a pickaxe, but by a gentle stream of light. Modern archaeology has moved far beyond simply unearthing these ancient conduits. Today, a new generation of detectives, armed with tools the Romans could never have dreamed of, is peering inside the joints without ever breaking the seal. One of the most revealing techniques is industrial endoscopy. Imagine a flexible fiber optic cable, thinner than a pencil, fitted with a tiny camera and a brilliant LED light. An archaeologist can carefully thread this probe into the open end of a lead fistula still embedded in a wall, or down into the mouth of a terracotta drain. As the camera snakes through the dark interior, it transmits a live video feed to a monitor above ground. For the first time in 2 millennia, human eyes can see the inside of a Roman pipe joint as it was left by the plumbarius. The camera might reveal the smooth, concave fillet of a perfect solder seam, glinting in the artificial light. It might show the rough, crystalline texture of pozzolana mortar packed into a bell joint, or even catch the shadow of a forgotten tool mark left by the craftsman's thumb as he smoothed the seal. This non-invasive look allows researchers to assess the quality of the workmanship, identify different repair techniques, and even discover blockages or mineral deposits that tell a story about the water's journey and the pipe's final days. It turns a solid object into a living tunnel, letting us travel back through time without disturbing a single grain of ancient dust. Beyond sight, science delves into the very essence of the material. Metallurgical analysis takes a microscopic approach. Researchers can take a tiny, carefully extracted sample from a lead pipe, perhaps from a broken edge or a discrete area already damaged. In a lab, this sample is mounted, polished, and placed under powerful scanning electron microscopes. At magnifications thousands of times greater than the naked eye can see, the metal story unfolds. The analysis can reveal the grain structure of the lead, showing how it was worked, whether it was cast, hammered, or annealed. It can detect the precise alloy composition of a solder joint, measuring the percentages of lead and tin, and even identify trace elements that act like a chemical fingerprint, pointing to the specific mine the ore came from, whether it was in Britain, Spain, or Greece. This tells us not just how they built it, but where the empire's raw materials flowed from, mapping a hidden economy of extraction and trade. For terracotta, similar analysis of the clay fabric and mineral inclusions can pinpoint the local workshop that produced the pipes, revealing the scale and standardization of this ancient industry. Perhaps the most transformative tool is three-dimensional laser scanning. When a complex section of plumbing is uncovered, perhaps a nest of lead pipes in a bathhouse or a junction in a distribution tank, archaeologists can now preserve it digitally in perfect, measurable detail. A laser scanner, set up on a tripod, projects millions of points of light on the surfaces, recording their exact position in space. It creates a breathtakingly precise point cloud model that can be rotated, measured, and explored on a computer screen. This digital twin is permanent. It allows engineers to run virtual simulations, testing water flow and pressure dynamics through the ancient network. They can calculate if a particular joint was under stress, or if the system's design was optimized for efficiency. The scan can also be used to create a physical replica through 3D printing, letting modern craftsmen attempt to recreate the soldering or mortaring techniques with their own hands, feeling the challenges and skills required. This process of reverse engineering through digital and physical models bridges a 2,000-year gap, transforming ancient artifacts into active blueprints. The goal of all this high-tech scrutiny is profoundly human, to recover the lost knowledge in the hands. By combining endoscopic views of interior seams, microscopic data on alloy mixtures, and perfect digital models of complex assemblies, researchers are piecing together the Roman plumber's mental toolkit. They are learning the precise temperature range needed for their solder to flow correctly, the exact consistency of the mortar that would set underwater, and the subtle hammering technique that could cold weld lead without cracking it. Each scan and spectrum is like recovering a single page from a lost manual. This isn't just about admiring their work. It is about understanding the decision-making process behind every flare of a bell, every brush of flux, and every tap of the hammer. In the silent, corroded pipes, modern science is listening for the echo of an ancient craftsman's skill, slowly learning to speak the lost language of watertight stone and metal all over again. The ghost of the plumbarius never truly left us. His soldering iron may have grown cold, but his fundamental solutions were simply waiting to be rediscovered and reborn in new materials. The direct line from a Roman workshop to your own basement plumbing is astonishingly clear, a legacy written not in grand arches, but in the quiet logic of connection. Take the very concept of a pressurized municipal water system. Before Rome, civilizations moved water through open channels or simple gravity-fed conduits. The Romans pioneered the idea of a closed, pressurized network, using the relentless force of gravity over distance to push water up into buildings. through narrow pipes and out of fixtures. This radical notion that water could be forced to go where you wanted it, not just where it naturally flowed, is the bedrock of every modern city's water supply. When you turn on your kitchen tap, you are activating the final link in a chain of engineering that traces straight back to the Castellum Divisorium of ancient Rome, where water was first divided and dispatched under pressure into the urban fabric. That pressure demanded secure joints, and here the legacy is even more tangible. The Roman use of solder, that meticulous alloy of lead and tin applied with heat and flux, is the direct ancestor of the solder used by modern plumbers for copper pipes. The technique is virtually identical. A modern technician still cleans the pipe, applies a flux to prevent oxidation, heats the joint with a torch, and watches as the capillary action draws the molten solder into the seam. While we have thankfully swapped toxic lead for safer tin silver or lead-free alloys, the physics and the craftsmanship remain a 2,000-year-old echo. The goal is still that smooth, concave fillet of metal, a perfect, watertight seal born in the fires of Roman foundries. Then there is the idea of standardization. The Roman fistula came in predictable diameters, and their terracotta pipes used the modular bell and spigot system. This was not accidental. It was the beginning of industrial-scale infrastructure. It meant a pipe made in one workshop could connect to a pipe made in another, that repairs could be made with interchangeable parts, and that large projects could be planned with reliable dimensions. This principle is the soul of modern plumbing. Today, we have globally standardized pipe diameters, thread types, and fitting geometries. A half-inch copper pipe from any manufacturer in the world will fit a standard half-inch fitting. This universal language of measurement, which allows a house in Tokyo, Toronto, or Tunis to be plumbed with compatible parts, finds its first coherent grammar in the stamped and measured lead sheets of the Roman Empire. Even the humble toilet tells a story of inherited design. The Romans mastered the simple, efficient wash-out latrine, using a continuous stream of water from an aqueduct branch to flush waste through a terracotta drain and into a sewer. The basic silhouette and hydraulic principle, a bowl, a water channel, and a downward sloping drain, are eerily familiar. While the flush mechanism as we know it took more centuries to evolve, the foundational idea of using flowing water to rapidly remove waste from an indoor space was a Roman innovation that never completely vanished from engineering memory. Our modern world is built upon these rediscovered secrets. The next time you hear water rush through your walls, or watch a plumber seal a joint with a puff of smoke from his torch, you are witnessing the living legacy of an empire that decided a civilization could be held together, one perfect connection at a time. Yet for all our high-tech scans and microscopic analysis, some secrets of the Roman plumber still slip through our fingers. We can see the perfect solder seam, but we cannot hear the whispered shop talk, the guild secrets passed from master to apprentice. How, for instance, did they achieve such flawless, consistent soldering without the pinpoint control of a modern propane torch? Their heavy iron irons, heated in a charcoal brazier, were crude instruments. Maintaining the exact temperature needed to melt the lead tin alloy without overheating and damaging the thin pipe wall was an art form lost to time. Was it the rhythm of their heating, moving the iron in and out of the coals with an intuitive sense of timing? Did they have secret flux formulas, beyond simple pine resin, that gave them a wider margin for error? The uniformity of the joints we find suggests a standardized, repeatable technique, a craft honed to a science, but the precise steps of that dance remain a mystery. This leads to the tantalizing possibility of guild knowledge. Roman craftsmen were often organized into collegia, professional associations that guarded their methods closely. The plumbarii would have been no different. Within their workshops, masters likely held closely guarded tricks, perhaps a specific way to hammer a cold weld that produced a finer grain, or a proprietary mortar additive that made it set faster underwater. These were not written down in manuals, but taught through demonstration, through the feel of the hammer in the hand and the sight of the solder as it began to flow. The loss of these living libraries, when the empire's economic and social structures collapsed, may have erased nuances of the craft that our machines cannot reconstruct. We see the magnificent result, but the subtle human wisdom that consistently produced it is gone. And what of the methods we have simply never found? Our understanding of Roman engineering is built from the fragments that survived, the pipes buried in volcanic ash, or those preserved in the dry soils of frontier forts. But what about the joinery of the temporary, the experimental, or the purely local? In a sprawling empire that lasted centuries, there must have been countless regional innovations, clever fixes devised by a lone plumbarius in a distant province to solve a unique problem. Perhaps they used a locally abundant tree resin as a sealant, or developed a wooden clamping system for quick repairs that has long since rotted away. These undocumented, ephemeral solutions are the true ghosts of the archaeological record. They hint at a universe of practical ingenuity that existed outside the standard models, a shadow history of engineering waiting to be discovered in some yet unexcavated workshop, midden, or forgotten military outpost. The greatest secret of Roman pipe joinery may not be the one we can see in the museum case, but the one we have not yet thought to look for. So the soldering iron cools, and the last echoes of the hammer fade. The story of Roman pipe joinery is a chronicle of hidden connections, a testament to an empire that understood strength lies not just in the grand arch, but in the perfect seam. They engineered resilience into every material, from the cold welded lead of a pressurized main to the flexible, breathing mortar of a terracotta drain. This was more than plumbing. It was a philosophy of permanence, a belief that civilization itself could be bound together by watertight stone and metal. Their work supported the daily rhythms of millions, turning mountain springs into street fountains and bathhouse steam, enabling the very urban life that defined Rome. Today, 2,000 years later, we still measure our own engineering against the quiet endurance of their pipes. The next time you walk through an old European city, look down. The pattern of the cobblestones might follow an ancient road, and beneath your feet, in the silent dark, the ghosts of their terracotta drains may still be carrying the rain away. Or gaze at the robust simplicity of a modern soldered joint, and see the direct lineage from a Roman workshop. Their secrets, once lost, now form the foundation of our own world. If you have ever spotted a remnant of Roman engineering in your city, or if this hidden history of connection has sparked a thought, share it below. The conversation, like the water, should keep flowing.